Yeah. Thanks for the introduction. Today I would like to present our result on mobile computation offloading. The title of our paper is Enabling Precise Offloading for Commercial Off-the-Shelf Binaries. My collaborator is Jungyu and Mia Zhai, and this is my comment from the University of Minnesota, and Yufeng Jiang from Intel. Nowadays, people increasingly rely on their smartphones and tablets for completing more and more sophisticated applications, such as image processing, 3D games, and even virtual reality. However, most mobile and IoT devices suffer from low computing capability and limited battery life. A recent study showed that a mobile device is more than 5 times slower than a desktop computer when needed to make the same chess game. And almost 90% respondents in a survey rated long battery life was one of the top features that considered when buying a new smartphone. This indicates that battery life is very important to the success of commercial mobile devices. So, how to improve the performance of mobile applications and prolong the battery life of mobile devices is a big challenge of mobile computing. There are several different approaches to overcome this challenge. Mobile computation offloading has been demonstrated to be a very effective way to prolong the battery life at the same time of improving the performance of mobile applications. In a computation offloading system, the computation-intensive tasks on a mobile device are sent to a more powerful server and executed remotely on the server. After the server finishes the execution, the results are sent back to the client. Considering the more powerful computing capability of the server, the performance of the offloaded application and the battery energy, the performance of the offloaded application can be improved and the battery energy of the mobile device can be conserved. Although mobile computation offloading can be very effective, there are still some obstacles to design a practical offloading system. One of the biggest obstacles is that how to tackle the differences in the instruction set architecture between the client and the server. For example, we may have an ARM mobile device and an x86-64 server. So the offloading system should be able to execute the ARM application on the x86 machine. To achieve this goal, most of existing offloading systems rely on language-level virtual machines, such as Android W Java virtual machine and the Microsoft .NET Common Language Runtime. However, this approach cannot offload the native mobile application using native library because they often tie closely to the specific programming language and their runtime. Moreover, the trend of this language-level virtual machine is that they incorporate more native binary code so that they can be more adaptive in the native environment or meet the performance requirements. For example, the Android Art runtime. Also, another recent study showed that 1/3 of the top 20 Android apps, open source Android apps, contain more than 50% of native code and spend more than 20% of their execute time in the native code. Some other offloading system simply recompile the offloaded application for the server item to achieve the offloading functionality. Obviously, their applicabilities are limited to the availability of the source code, which is usually unavailable in practice due to the commercial reasons. So we need a system to offload the natural binary application from the client to the server without the requirement of the source code. To overcome the limitations of existing offloading system, we propose to extend the capability of dynamic binary translation across the client and server boundary and automatically offload the identified computation-intensive binary code region and their memory data from the client and the server. This graph shows the framework of our offloading system. On the left, the client side, we have offline profiler and a dynamic binary optimizer. The offline profiler dynamically increments the binary code and collect profiling information, which is used to identify code region for offloading. The dynamic binary optimizer rewrites the original binary code to send offloading requests to the server. On the right server side, we have a dynamic binary translator, which is used to respond to the offloading requests from the client and emulate the client binary code. With this framework, our system can offload the native binary application from the client to the server, even if they have different SR. Now let's see some design issue in our offloading system. The first design issue is how to select the code region for offloading. Our offloading system utilizes the offline profiling and function level granularity to identify binary code region suitable for offloading. For each function, we collect extreme time, dynamic memory allocation, deallocation, memory accessing, I/O activity, and polycontext information. Based on this information, the most time-consuming functions are included in the initial offloading target set. However, the extreme time is not the only concern, because some of the targets in the initial offloading target set may have very large live in or live out data sets, or very intensive I/O activities, which can incur very large communication overhead between the client and the server, and offset the benefit of the offloading. To avoid this problem, our offloading system realistically extends the initial offloading target set to include the functions that generate or consume the live in or live out data used or produced by the targets in the initial target set. It may also exclude the targets in the initial target set that have very intensive I/O activities to avoid the high communication overhead. By this way, our offloading system can minimize the communication overhead between the client and server. For more details about technical perspective of offloading, we refer to the first algorithm in our paper. To guarantee the correct execution of the offloaded application, the memory must be maintained coherent between the client and the server. To meet this requirement, our offloading system maintains the same memory layout between the client and server, which means each time one new memory region is dynamically allocated or an old memory region is deallocated on one side, the other side is informed to perform the same operation. And the memory coherence is maintained at the page level to take advantage of the page access mechanism provided by the operating system. And also the memory pages are fetched on demand to avoid the unnecessary communication overhead between the client and the server. A significant limitation of existing offloading system is that most of them try to avoid offloading code region with I/O activities. However, as we know, it is quite common to have I/O operations in mobile applications, for example, reading or writing a log file. Since most of the I/O operations are realized by invoking system call, our offloading system classifies the system call into 3 categories and handle each category in a different way. In the first category, the system calls are emulated on the server side, because the actual results of these system calls are generally same or similar to the client and server. In the second category, the system calls are sent back to the client and execute on the client. For example, the open system call should open the file on the client instead of the server. In the last category, the system calls are executed on both the client and the server. For example, the memory map, or memory unmap system call, which are usually related to dynamic memory allocation and deallocation. Moreover, to reduce the communication overhead involved in the I/O activity, our offloading system also try to buffer the results of the I/O operation until they have to be set. Like this way, our offloading system can seamlessly offload binary capability with I/O operations. We have implemented our offloading system based on HQMU, which is a retargetable dynamic binary translating system based on QEMU. We evaluated our system using back in 2006 with the trying input 6 benchmarks similar to the real-world application, including game and JavaScript engine. Our experimental platform includes x86 server and ARM development board as the client. The connection between the client and the server is a public wireless network. Now let's see some experimental results of our system. This graph shows the performance results of our system. For each application, we have 3 parts. The first part is the baseline, which is the native execution on the client without offloading. The second part is the performance result achieved by our offloading system. The last part is the performance results of using HQMU to run the evaluated application on the server without offloading. So, which is considered as performance outcome of our system because there is no network communication overhead. We also separated the performance results from spec signal services to avoid skewing the overall performance result. Because most of the applications in this benchmark suite are computation intensive. Also, in the evaluated application, the SpiderMonkey is a JavaScript engine. It is quite difficult for existing offloading system to offload this application because it may dynamically generate native binary code. To show you this graph, you can see our offloading system can achieve 1.9 times speed up for the real-world application and 1.6 times speed up for the spec 6. This demonstrates that our offloading system is quite effective to offload the native binary application. Now let's see some energy consumption results of our system. I'll show you in the graph. On the left side, our offloading system can reduce 49% energy consumption on the client for the real-world application, and 42% for the spec in 2006. The graph on the right side shows the power consumption of native and offloading execution on the client for the full game. The difference of the 2 lines is the power consumption reduced by our offloading system. As expected, our offloading system can reduce the power consumption on the client side because the computation intensive code can be offloaded to the server. We also studied the sensitivity of our system on the network analysis. Please refer to section 5.3 in our paper for more details. Here are the conclusion of our work. We intended the capability of cross-isodynamic binary translation to offload the identified computation-intensive binary code region from the client to the server. We also discussed the design issue in our offloading system, including packet selection for offloading, memory mapping between the client and server, and the I/O operation and system costs. Experimental results show that our proposal system can address this issue effectively. This is my thanks for